Hello and welcome to another fun time with Trig with Mr. Meyer from the Way Happy Studios here in Livermore. We are going to talk about multi-angle identities, and there's a bunch of them this time. So I'm sorry, and I got no clever songs. I got nothing. Just memorize. So there's your first. What is that? One, two, three, four, five. First five right there are called the double angle. Now the funny thing about the double angle ones is that they could all be derived from your sum and difference. So, if on the off chance you were like, I can't remember the double angle, you could always go back and do sum and difference. And in fact, I'm going to talk right now about proving cosine of 2x, showing you that it does turn into one of these three formulas here. Notice, by the way, that cosine has three different ways. That's just because you could replace cosine squared with 1 minus sine squared, or you could replace the sine squared with 1 minus cosine squared, and you would get the other two. So they're really nothing too fancy. They are just re-derived of the same formula. But let's see how you'd get one of those. So look at cosine 2x, right? If I think of 2x just as x plus x, which it is, then I could use my sum and difference formula. I could say cosine of x plus x. Well, wait a tick. I know that formula, right? That's cosine, cosine, sine, sine. And so cosine minus sine, and right off the bat, you see what you get. Cosine squared of x minus sine squared of x, and you're like, whoa, we just proved it. So isn't that beautiful? It's that quick, it's that easy. In fact, all of them are that easy. You could try proving sine of the double angle if you'd like, or tangent of the double angle even, and you will get your identities. And that is your double angle formula. There's 5 of them. So 2 sine x cosine x, or in this book uses u, so 2 sine u cosine u, or you could use any of the 3 cosine ones. You get to pick. It's your choice. Usually if I see something with sines and cosines, I'm going to pick that one. Usually if I see something with cosines or just a 1, I'm going to pick that one. If I see something with sines, I'm going to pick that one unless it has a 1 in it that I want to cancel. So that's kind of why there's the 3, and you can pick and choose. So there's your double angles. Great answers. Now what about the power reducing identities? Now these ones, sometimes we have an exponent that's too big and we wish it was smaller, and there is a power reducing. So you can see if you have sine squared of u, you can change that to 1 minus the cosine of the double angle all over 2. And you can do the same thing with cosine squared and tangent squared. They all have their own formulas, so not a big deal. Now let's show you how to do one. So here I have sine to the 4th power. Wow, so big, and we've run into that in class where we have these big exponents. We wish we could make them smaller. Well, now we can, and so here I go. First thing I would do is I can't do sine to the 4th, but I can do sine squared. So let's just change that to sine squared x times sine squared x. And now I'll power formula this guy down right here. It'll be 1 minus the cosine, using the formula, 2x all over 2. And I have 2 of those, so I'm just going to square it out of laziness. Maybe I should have written it side by side now that I think about it. In fact, I will. I'll write it side by side since there's 2 of them, because I think I'm going to FOIL out that top. Now the whole goal, by the way, I probably should have mentioned what I'm doing here, is that they want me to get this with no powers greater than 1. So sometimes a kid will say, well then wait, can't we just do sine x times sine x times sine x times sine x? Those are all powers less than 1, finished. Well, no, because that would all get multiplied back together and just get you right back to sine to the 4th. So we can't have that. We can't have any multiplying. We'd have to have addition and subtraction so that we can't combine like terms. So that's what we're trying to get at here. And so notice you might be like, hey, wait a minute, you just got it all down to linears, cosine to the 1st power. But again, they're multiplied together. If you FOIL this out, you're going to get a cosine squared. But you're kind of right, because we've gotten rid of a lot of it. So let's see. If we FOIL this out, I would have 1, then minus cosine 2x and minus cosine 2x right behind it. So minus 2 of the cosine of 2x's. And then, here's the bad one, plus cosine squared of 2x. Now that was the bad guy, right? All over 4. Now at that point you're feeling pretty good. You've almost gotten rid of all of them. And what I mean by that is give the 4 to everybody. You would have 1/4 minus 2 cosine 2x over 4, which those can reduce. And you'd have plus cosine squared 2x all over 4. So notice you just got a bunch of things added together that look pretty nice. In fact, I'm going to erase this 2/4 so I can get it to 1/2, so it looks a little better. Now that looks all good except for right here, this darn power. So we'll do it again, right? We had a to the 4th power. Now we're down to the squared. So we'll just do it again. Now the big trick here is this. That is a power reducing formula. But look right here. There's a 2x where on the formula there's just a u. So we just got to be careful that wherever we see the u in the formula, we're going to replace it with a 2x. It's not going to be a big deal, but just make sure we're aware of it. So here we go, last step really. I have the 1/4 minus the, if you want, you could do 1/2 cosine 2x just so it looks kind of pretty. And you could even pull out the 1/4, and now you'd have the cosine formula that you need. Oh gosh. 1 plus the cosine, now remember here comes that 2, so it's 2 times 2x, let's call it 4x, all over 2. And you've actually completed the last step. You're golden there, right? So I think I could just maybe rewrite this a little prettier. What could I do? 1/4 minus 1/2 cosine of 2x, I guess, plus, what do you want to call that? 1, I guess I could multiply the 4 back in. 1 plus cosine of 4x all over 8. And there it is. Notice no powers greater than 1. They're all nice linear powers. And now we're done. That's how we know we're finished, when they want us to have no powers greater than 1. Awesome. Notice I'm not going to ask you to try one because you all say that's weird. So I'm just going to be quiet for a second. Wow, great effort. Keep up the good work. So now, last but not least of identities for the day, you got some more. These are called the half-angle identities. Whew, look at them. They are a pain, and they are tricky, right? Notice in the identity you use a u, but out here you have a u over 2. It's very important to understand what's going on. That inside the square root is a number that you should be able to take the cosine of. So it's probably one of your favorites, like a 30, a 45, a 60, a 90, something like that. On the outside, though, it would, on the other side, on the left-hand side, they're probably asking you one of your favorites divided by 2. So you have to be very careful. You have to figure out what that u value is. So kind of what I mean by that is, look at this problem. They're asking me to figure out what sine of 22.5 is, degrees. Well, if I know that I want to use the half-angle formula, that means that, this unknown angle, let's call it a x, I know that's true. Well, look at this point. We can drop the signs and we can say, well, we know 22.5 has to equal x over 2, which means 45 must equal x. That's what's going to go in the formula. 45 degrees is what's going to go in there. And then we just go ahead and solve it. Now, these can get nasty. They can have double radicals in them, so you're going to be like, crazy. But don't panic. Also, you got to think about the plus or minus up front. The plus or minus, you will just decide if it's positive or negative according to all students take calculus. So that's all I want to worry about. I know I'm going to do sine of 22.5. I will write this kind of funny. Sine of 22.5 we figured out is 45 over 2. And so I know that 22 degrees is in quadrant 1 where everybody's positive, so my answer is positive. Now I'm just going to go ahead and go to the formula. So here we go. We know it's positive. We know it's the square root of 1 minus the cosine of 45 degrees all over 2. Now we know the cosine of 45 degrees is 1 minus root 2 over 2 all over 2, all square rooted. There's that gross nesting. But let's just try to clean it up best we can. Maybe I'll get a common denominator here up in that numerator, so I'll call this 2 over 2. So now look what we have. We have 2 minus root 2 all over 2 all over 2 square rooted. All right, not too bad. probably a good time to copy dot flip, right? So let's copy the top, 2 minus root 2 all over 2. Change it to dot. Now be careful, flip the bottom. The bottom is a 2. So when you flip it, it's going to be a 1/2. And all of that, of course, is under a square root. Well, good news is we got 2 minus root 2 all over 4, all under a square root. And we're almost out of here. That square root, we do know the square root of 4. So we could call this 2 minus root 2 all over 2. Almost said 4. Square root of 4, which is 2. And there's my exact value of sine of 22.5. Crazy, right? But doable. Okay, and now finally some solving. Now, just a little heads up, we are going to solve. Now, there's many answers to trig identities because of coterminal angles. So notice right here, I restrict you. I just say, hey, give me the answers between 0 and 2 pi. So just one revolution, tell me the answers. Because, again, there's multiple answers, and so I got to be careful. Otherwise, your answer's got to have that whole plus 2 pi n thing and stuff like that. And we could talk about that in class if you're scared. But solving is not so bad. Just remember that usually when you want to solve something, it's really nice if you have it equal to 0, because then you can always set your factors equal to 0 and you can solve them, and you'd be like, oh, one answer is 0 and one answer is 1. And you're like, yay. Well, that's going to be the same thing for our trig identities. We're going to wish that some of these things equal 0. So here I go. Notice right off the bat, I would love to solve this. However, the problem being is that it's not equal to 0. So I can't divide both sides by sine, because we all know that sometimes that would be dividing by 0. So we're just going to subtract it. So I have sine of double angle minus sine of the single angle equals 0. Now that's sweet if I could just factor something out. Now you would almost want to factor out a sine x, but you can't because of that darn double angle right there. So I will change that double angle. There's only one choice. To sine x cosine x, remember that's the one you learned up at the beginning, minus a sine x, and lo and behold, you've noticed something. They both have a sine x in them. Let's pull it out. Sine x times 2 cosine x minus 1 equals 0. And we got nice linear factors that equal 0. We're golden, right? We know at one point sine x equals 0, and I can use the hand trick or the unit circle to figure out when that is. Now, sine again is the bottom, so to be 0, that would be a 0 degree angle. So that would happen at 0 degrees. I believe that would also happen at 180 degrees. Oh, wait, they wanted radians, so 0 and pi would be my two answers for that, right? Because they wanted radians. Also, another time that this is equal to 0 is 2 cosine of x minus 1 equals 0. So move the 1 over. 2 cosine of x equals 1. Divide by 2. When does cosine x equal a half? So back to my hand trick. That would be at pi over 3. But wait. It's also, all students take calculus, that's also going to be positive a half down there in quadrant 4, where the reference angle is pi over 3. So therefore I would say negative pi over 3, but oh darn it, they want the answer between 0 and 2 pi. So what is that? 2 pi is like 6 pi over 3. So let's subtract off that pi over 3. So the other answer would be 5 pi over 3. So there's all our answers on or between 0 and 2 pi. We have the answers would be 0, pi, pi over 3, 5 pi over 3. I guess I could put them in order, but you get the idea. Nice. All right, what about that last one? Let's do one more solving. It's already equal to 0. That's awesome. I also noticed that I can't factor out a sine. This would be a great time to use a double angle formula. Remember, this one had 3 different choices. So you could do the sine squared minus cosine squared minus sine squared. But then I'd have cosines and sines. I remember one of them had just sine in it. So let me scroll up and get what it is. So cosine of 2x. If you notice, I could use 1 minus sine squared. So I'm going to use that, 1 minus 2 sine squared. So I'm going to come back here and I'm going to rewrite this as 1 minus 2 sine squared x minus sine x. Now the bad news is I thought I'd be able to factor something out. I can't. Can't move the 1 to the other side because then 1 equals 0. So you're like, dang it. Don't really see anything making me way happy at the moment, except for maybe it's factorable. So a little heads up, I'm going to write this in order. Now I don't like that this negative is in front of my sine squared term. So in essence, I'm going to move everybody to the other side. So it would look like this. 2 sine squared x plus sine x minus 1 equals 0. Now the big question is, does that factor? We got to think of this kind of as like 2x squared plus x minus 1. And you got to think, does that factor down? Well, the good news is yes, right? It does factor down. What two things multiply to negative 2 that add up to 1? That would be 2 and negative 1. Now, because of my method of bottoms up, I got to divide both these by 2. And I would have x plus 1, and I would have 2x minus 1. And those are our factors. Well, now let's throw the signs back in. Instead of x's, let's use signs. So we have sine x plus 1, and we have 2 sine x minus 1 equals 0. And now we just got to think about when that happens. So again, when does sine x equal negative 1? Well, according to our all students take calculus, there's a couple of quadrants there that might have it. So let's look. Oh, wait, negative 1. That's that crazy one. So I got to fold down what? 90 degrees? So this is a 90 degrees reference angle? No, gosh, they want pi over 2 again? But wait, pi over 2, that would be up here. That's when sine would definitely be positive. So if they want negative, it must be down here. That reference angle. So I know that's 3 pi over 2. And there's nobody else, right? That's the only one for that answer. Now over here, 2 sine x equals 1. Divide by 2. When does sine x equal positive a half? We're talking about quadrants 1 and 2. It must happen twice. So what are the 2 times that would happen? Well, that's definitely a 30-degree reference angle, or what we like to call pi over 6. And if it's over here in quadrant 2, then it's going to have a pi over 6 reference angle. That's going to be 5 pi over 6. And there's our answers. We have pi over 6, 5 pi over 6, 3 pi over 2 are all solutions. Good job. Stay happy.